Hello everyone, my name is Payam Morseli and I'm a second year PhD student here at the Peace Lab, Arizona State University. And today I want to talk about the hybrid SiC-based single stage microinverter that we have optimally designed here at the Peace Lab. So let's go to the details of how we are going to optimize this design. So let's start with the problem statement. As you can see here, this is the state of the art. You can see that we have one high frequency inverter here at the input, and we have a high frequency transformer that is connected to the rectifier. Then at the output of the rectifier, we have a high voltage DC that is maintained by high volume DC capacitors. And after these capacitors that you can see here, we have the inverter that is working usually in this state of the art at high frequency. And after that, through a filter, we are connecting the device to the grid. So here is the state of the art. As you can see, we have three main drawbacks here. The first one that I have mentioned is the fact that we are going to need a high volume DC capacitors here, which is the bulky capacitor. And the other one is the another bulky capacitor at the input that we are going to substitute this one with the PVB. So DC capacitors are generally realized by the electric capacitors, which decrease the reliability of the system. And another drawback of this configuration is the fact that we are working at high frequency here at the inverter, which is posing a lot of switching losses here. So this state of the art also includes an additional magnetic core, which is the power transfer inductance here at the input of the high frequency transformer, which also increases the losses because of the core losses and the conduction losses through the windings of this inductor. So this is a state of the art that you can see here. We have a one DC-DC generation here, and another one is the DC-AC inverter that you can see here. So we are going to design an optimal modulation and an optimal design for a 500 volt amperes and 220 and 60 volts input that is connected to the 120 volts RMS or 240 volts RMS AC voltage that is the grid working with 60 Hertz frequency. So as I have mentioned here, the objective of the design is the connection of a DC input, that is a solar panel, to the AC grid. And our proposed architecture is a single stage series resonant dual active bridge based DC-AC microinverter. So we have used the series resonant configuration here because it has inherently lower RMS current through the power transfer impedance, which also decreases the conduction losses. So the problems with the state of the art that I have mentioned are also stated here. You can see we had 380 full bridges here that are working all at high frequencies, and we have two bulky capacitors, which are mainly realized by the electric capacitors that decreases the reliability of the system, and we have an additional magnetic core in the DC-DC power transfer. So basically, we are going to address these problems by substitution of one of the active full bridges, that is the inverter, with an off-voltage stage that is switching at 60 Hertz frequency, which reduces the switching losses. And we are going to substitute the input bulky capacitor with the PVB or Power Pulsating Buffer. And we are also going to substitute the bulky capacitor at the intermediate section of the of a DC-DC operation and a DC-AC operation with a less volume capacitors, which decreases the volume of the system. And the last one would be that we are going to substitute the actual magnetic inductance at the input of the power transformer. We're going to substitute that one with the leakage inductance of the transformer. So here you see how we are going to integrate all those proposed solutions into one configuration that you can see here. So basically we have changed the input capacitance with the power pulsating buffer that you can see here. And we have this primary bridge that is realized by the GaN devices, and the same thing happens for the secondary bridge. And lastly, we have the on-voltage stage that is switching at 60 Hertz line frequency, which also reduces the switching losses. So before we start, let's see how many modes of operation exist for all the DABs in the literature. So all the DABs in the literature, they have 3 different degrees of freedom. One of them is the phi, which is the phase shift between the primary bridge leading leg and the secondary bridge leading leg. This is the main control variable that all the DABs use. And the second one and the third one is delta 1 and delta 2, which are the phase shift between the primary bridge legs and the phase shift between the secondary bridge legs, respectively. So if we use all these 3 degrees of freedom, we're gonna call our modulation technique a triple phase shift, which is the technique that we are going to use here because it offers us with a lot of degrees of freedom. So technically, we are able to reduce the current, the RMS current through the transformer windings even more. But before we go forward, we need to know how the current through the transformer winding is varying with those the modulation variables, delta 1, delta 2, and phi. So here we see that the voltage at the input and at the output of the LC tank is presented with the GHA model, General Harmonic Approximation, as you can see here. And the current through this LC tank or through the transformer windings that you can see here is adhering to this second order equation here. So if we put these equations for V1 and V2 into this second order equation, we will be able to find the time varying equation of the current through the LC tank, which is provided here. So basically, this if we have this one, we are able to find the RMS current based on this equation that you can see here. However, this will provide us with the current equation for the DC operation of any DAB that is present. But we are aiming at the generation of the AC voltage here at this intermediate section that you can see here. So how are we going to do that? So the aim here is that we want to generate a rectified sine wave voltage waveform here before the unfolded stage. So our approach is to divide these 60 Hz line cycle that you can see here into a certain number of intervals, where we can actually assume the operation of a DAB in each of those intervals as a DC-DC operation. So basically, in each of those operation points, intervals, we will have a certain and constant values of delta 1, delta 2, and phi. Which is definitely different from the other intervals. So if we find the RMS current for each of these intervals, we will be able to find the RMS current over the 60 Hz line cycle through this equation that you can see here. So this will provide us with our final objective function, which are going to minimize, because we want to minimize the RMS we want to minimize the conduction loss of the system, right? So basically, if we minimize the RMS current here that you can see here, we will be minimizing the conduction losses of the system. However, in addition to the loss optimization, we believe that the design optimization should be also taken into consideration. So here I have provided the power impedance optimization that you can see here. So as you recall, I have mentioned that the LC tank configuration is providing an inherently lower RMS current through the device. So this is due to the fact that the impedance of the SRDAB or the LC tank is provided by this equation that you can see here. So you can see here that as the frequency increases, or let's say as we're going towards the higher order harmonics of the current, the equivalent inductance of the LC tank limits to this resonant inductance that you can see here, which is presenting a higher value of the inductance with respect to the one that is presented here for the single inductor DABs. So that means the LC tank configuration is suppressing the current through the LC tank for higher order harmonics of the current. So that means the summation of all those harmonics will lead to the lower value as compared to the single inductance configuration. So here you see that the locus of the current through the power transfer impedance for the LC tank is lower than the one that we were experiencing for the single inductor at all times. You can see here, this axis represents the output power and this axis is representing the voltage gain. So this will be one optimization that we have taken into account. And the other one would be the fact that we are also optimizing the actual values of the L and C that are in the tank. So here you can see that if we increase the ratio of the actual inductance to the equivalent inductance of the LC tank, we are reducing the RMS current through the LC tank. So that means like at some certain point we are experiencing the lowest value of the RMS current. Another design optimization would be the fact that instead of going to for the optimization of the equivalent inductance of a system that is generally used in the literature, we are taking the whole value of the product of the N and L as one variable. So basically that means we are taking the transformer turns ratio, or N, as an additional variable here that we can take into consideration for the optimization of a system. So basically we can see that we can increase or decrease the value of the inductance by decrease or increasing the value of the transformer turns ratio. To show this effect, you can see here this chart that you can see here. So the RMS current through the transformer windings for the 60 Hz line cycle is variable for different sets of the inductance values and the transformer turns ratio. So basically you can see that, for example, for 2.5 microhenries as the power transfer impedance, we are experiencing the lowest value of the current through the LC tank when the transformer turns ratio is equal to 2.4. So that means different sets of transformer turns ratio and different sets of the inductance, equivalent inductance, would lead to different values of the RMS current. So that is an additional point of consideration that we have taken to find the optimized design of the system. So here is a 3D figure of the point that I have mentioned already. So you can see how the instantaneous current through the transformer windings is varying for different values of the transformer turns ratio and for different values of the output voltage phase. So you can see that at some certain point, for example here 3.2, transformer turns ratio equals to 3.2, we are experiencing the lowest value of the RMS current. And for some certain transformer turns ratio value, we are not able to transfer the power through the device at the peak gain, where the power transfer is the highest. So here you can see that we have also compared these three different modulation techniques: triple phase shift, dual phase shift, and the single phase shift for this operation, like a specific operation mode that you can see here. So basically we are realizing from this plot that the difference between the triple phase shift and the single phase shift is much higher at the light load, where we are experiencing a lot of current actually that is not shown here. Later in the figures you're going to see that. So this shows that at the 20% rated load we're going to have around 50% higher efficiency if we use the triple phase shift modulation, which is a technique that we are using in this design. So in addition to the conduction loss, ZVS loss or the switching losses are also really important. So in order to tackle the ZVS losses, the switching losses I mean, we need to pose two limitations on the current actually. So you see that in order to achieve the ZVS or the zero voltage switching, we need to have a proper amount of the inductive energy in the LC tank so that it is able to discharge the body capacitances of the switches. Another limitation is the fact that we need to have a proper direction for the current as well. So that means the direction of the current should be in favor. So we need to provide the switching instance considering the modulation variables, the switching instance based on the modulation variables, so that we can actually apply these switching instance into the current equation that we have provided earlier and achieve the values of the modulation variables that provides us also with the ZVS. That means like it also activates the ZVS for the switches. So if we take the ZVS limitations also into consideration, we see that the regions that the ZVS is activated is higher for with this assumption. So you can see here with the figure A and B, the ZVS limitation is taken into consideration, and with the figure C and D, the ZVS limitations are not taken into consideration. So you can see that the yellow region, which shows the activation of the ZVS at that particular point, is much higher when the limitations are posed to the current equation. So here, picture A and C are for S1 and 2, switches S1 and S2, and picture D and B, or vice versa, B and D are for the switches S3 and S4. So this advanced triple phase shift modulation is also verified using the simulation environment, where you can see that at the peak voltage gain, where we need to transfer around 100 kilowatts of power, we are experiencing a lower maximum of the current through the transformer windings with the LC configuration and with the optimized modulation. So you can see here that the maximum current also is limited. For example, with the single inductor that you can see here, the maximum current through the transformer windings is 38.2 amperes. However, for the LC tank configuration and with the optimized modulation, we are experiencing 33.3 maximum current. So that means like we require switches with lower switching ratings, actually current ratings. And now that we have optimally designed the device, we also have we fabricated this hardware that you can see here in our lab. So basically here you can see that this is the unfolded resistors that are realized by the SiC MOSFETs, because we are switching at 60 Hz line frequency. Here you see the secondary bridge that are the GaN devices, and here under the heatsink you see the primary bridge, which is also the GaN devices. And here in our design, you can see that the maximum height of a system is corresponding to the microcontroller itself. So basically that means all the devices here are working and are designed at the optimal value. So the control logic consists of three variables that I have mentioned, delta 1, delta 2, and phi. So I have provided all these delta values for the whole 60 Hz line cycle, and I have found these delta 1, delta 2, and phi values that optimize the performance of a DAV over the 60 Hz line cycle. However, we cannot use those values offline, and we cannot like feed the lookup table to the microcontroller itself. So I have used the regression model to provide an equation here that you can see, to provide the equation that mimics the behavior and the change of the delta 1 over the 60 Hz line cycle. That is this equation that you can see here. So this equation is actually the thing that is fed to the microcontroller. So this equation is variable with the input voltage and the output voltage. The output power, which mimics the behavior of delta 1. The same control logic also applies to delta 2, which with different set of equations that you can see here. So with these two equations, we are able to mimic the behavior of delta 1 and delta 2 based on the input voltage and based on the output power. So these two equations are a function of the input voltage and the output power. However, the phi itself is being controlled by a closed loop control that you can see here, a PI controller. And then after that, all these values of the phi, delta 1 and delta 2 that are provided based on the operation point of the system are going to the microcontroller itself, and the phase shift actually that are provided in the time domain are going to be applied to the switches. So with the hardware, we have actually verified the findings that we had earlier in our mathematical representation of the current. You can see that the actual current through the device that you can see with the green waveform here and here are completely adhering to the equations and the waveforms that we had earlier in our theoretical results and theoretical waveforms that you can see here. So basically that means that the equations that we have provided with the GHA model is also like completely fine with the hardware. Which results into the fact that the equations that we have provided for the conduction loss minimization and for the ZVS range activation is also valid. So basically you can see here that how the ZVS is activated for a better part of the cycle. That you can see here for different points of operation, the ZVS is activated thanks to the fact that our equation and our limitations on the equations are valid. So in addition to the verification of a ZVS range and the conduction loss minimization, I also have compared the conventional DAB with the single inductance and the SR-DAB that we have proposed in this proposal. So here we can see that the LC10 configuration that you can see here, these three bottom figures, with the optimized modulation is performing much better than the conventional DAB that is presented here. So here we are experiencing a lower RMS current with the LC10 configuration and with the optimized modulation, as well as lower zero voltage distortion that you can see here. For example, here this is for the single inductance or for the conventional DAB, and here we have the LC10 and the SR-DAB with the optimal modulation technique that you can see that we have a less zero voltage distortion. So that means we're going to experience and we're going to have a lower THD for this configuration. So you can see that how the THD performance is ameliorated with this configuration, where we have achieved a THD of 4.1%, which is less than the one that we had in the conventional DAB. Also, the efficiency of the system at the rated load is also around 1.2% better than the conventional DAB with the triple phase shift modulation. And additionally, you can see that this ATPS, the advanced TPS modulation with the SR-DAB and with the optimized design is performing and is showing a higher efficiency at all loads with compared as opposed to the one that we had in the conventional DAB with the single inductance. So in conclusion, we had for achievement in this proposal, we actually have optimized the modulation of the device with our limitations and with our current equations that we have provided theoretically, and we had the design optimization of a system that was consisting of the transformer turns ratio as well, in addition to the equivalent inductance optimization. Also, we reduce an additional and an actual magnetic core of the actual inductor by the realization of the power transfer inductance with the leakage of our transformer here that you can see, which leads to lower conduction loss, to lower core losses, and eventually higher efficiency. And finally, we have experimentally and also with the simulation, we have verified our findings, our theoretics, which verifies the fact that all these equations that we have provided and the cost function optimizations are valid. So thank you for watching this video, and I'm going to show you how these topologies and these optimizations are going to work in the lab. So here we see the hardware configuration of the SR-DAB that I have described in the slides. As you can see here, we have the DC input that is connected to the solar PV panels, and here we have the output of the board that is connected to the grid, which is 120 volts RMS. Here we have the microcontroller here, and you can see here this is the Power Pulsating Buffer, or the PPB, which is installed here to eliminate the electric capacitors here. So the design is for 10 millifarad DC link input capacitors, which is realized by three different electric capacitors, 3.3 millifarads each. and you can see that we can actually like substitute those electric capacitors with this PVB here. So the advantage of the PVB over the electric capacitors is that it reduces the volume, as you can see here. And the second advantage is that since we are having the ceramic capacitors here, we are increasing the reliability of the whole system by reducing or eliminating these electric capacitors here. So the primary bridge that I have described is here under these two heat sinks here, and then we have the input of the transformer here, then the transformer itself, and we have the secondary of the transformer, which is this pin and this pin. We have 4 switches at the secondary of the transformer, which is called the secondary bridge, and here you can see the gear driver circuit of the secondary bridge here. So after this secondary bridge here, we have the rectified sine wave voltage waveform here, that is here, which is in between of the secondary bridge of a DAB and the unfolder switch here. So the duty of this unfolder switch here is to unfold this rectified sine wave into a pure sine wave, which is then connected through an EMI filter to the grid. So since we are switching at 60 Hz here for this unfolder switch, we can realize the switches by the 6 MOSFETs, which is like less expensive. But here, for the primary and secondary of a DAB, we have to use the GaN devices because we are switching at 100 kilohertz. So in order to reduce the switching losses, we have to use these GaN devices here. So as I have mentioned earlier, we have to optimize the value of the transformer turns ratio here, the value of the power transfer impedance, which is realized by the leakage inductance of a transformer or an actual inductor in some designs, and the capacitors here. So this design is already optimized, and actually we have also optimized the modulation, which is modulation variables that are the phase shift between the primary bridge legs, that is delta 1 here, the phase shift between the secondary bridge legs, that is delta 2 or here, and we have the phase shift between the primary bridge leading leg and the secondary bridge leading leg, which is here and here, which is called phi. So once we have obtained in an offline manner, we have obtained these optimized value of the delta 1, delta 2, and phi over the 60 Hz line cycle, we can get the regression model of these values and feed the equation for delta 1 and delta 2 to this microcontroller here. However, the phi itself is actually controlled by the closed loop control. So here you see that I have connected these voltage probes here to the primary of the transformer. I have one current sensor here that is the primary that is connected to the windings of the primary of the transformer, and we have one voltage probe at the output of this converter. So here you can see the waveforms that are previously taken. You can see here, so this is the output of the converter. As you can see, we have a pure sine wave here, which is due to the design of this converter and the LC tank and realization of a power impedance by the LC tank instead of a single inductor. Here you see the current through the winding transformer windings, and you can see that the voltage at the primary of a transformer is like this, which is basically means that the delta 1 is activated because we have like these values, these like blue regions here. That means in these regions we have delta 1 activated. So as you can see, we have generated a pure sine wave with the aforementioned design and the aforementioned criteria that I have described in those slides.